Welcome to this presentation. My name is Alexander Lindermeier from the University of Bremen, and this is a joint work with Nicole Mego and Bertrand Simon. And the goal of this presentation is to give you an idea on how we can improve a very classic online algorithm for a very fundamental online problem using machine learned predictions. So first, let me introduce the problem, which is the K-server problem on a line. So yeah, let's imagine we have given some real line. Then the first part of the input of our problem is a sequence of n requests of points on this line. And the second part is a initial server configuration, which we denote by C0 and which tells us where our K servers are located in the beginning, and yeah, we write this as a K tuple. So in this example, we've given 5 requests, and our initial configuration is DD, which means that we have 2 servers located at D. Now the goal is to move the servers in a way such that they serve the requests in the order they appear in the sequence. So for example, in this example instance, we may move one server from D to C for the first request, then this server further to the second request to A, and for the third request at B, we move the other server, which is still at D, and we then end up, after serving 3 requests, in the configuration AB. And the objective is to minimize the total travel distance of the servers. And due to this objective, we will also assume that the servers are always ordered by their position on the line on these configuration tuples, because it makes no sense to move one server by another. Yes. So yeah, if we know the sequence of requests in advance, this is called offline setting, and there exists efficient algorithms to solve this problem optimally. Hence, we will look at the more interesting online setting. In the online setting, an online algorithm learns about the sequence of requests one by one. So at any point in time, it only knows the current locations of its servers and the current request it has to serve. And only if it serves the current request, it gets to know the next request or learns that there is no more request. And yeah, we use competitive analysis to analyze the performance of an online algorithm, where we say that an algorithm is alpha competitive if its costs are at most alpha times the cost of an optimal solution for the instance, where the optimal solution refers to the optimal offline solution, plus some additive constant, which is only allowed to depend on the initial configuration, and this has to hold for all instances. So let me give you some known results. So on the line, there's the classic and neat algorithm called double coverage, which is K competitive for having K servers, and it works as follows. Whenever a new request arrives, it moves the at most 2 closest servers of the request towards it with the same speed. And when one server reaches the request, both servers stop, which means that both servers will move the same distance and the closer server will eventually serve the request. And yeah, one can show for any metric space and any deterministic algorithm, but this algorithm would have a competitive ratio of at least K, which means that since the line is also a metric space, double coverage is an optimal online algorithm. Yeah, and for a general metric space, the best known algorithm is the work function algorithm, which is 2K minus 1 competitive. So there's still a gap between the upper and lower bound. But there's the famous K-server conjecture, which states that there exists a K competitive algorithm for the K-server problem. And if we allow randomization, we can actually get way better algorithms, and there's a polylog K algorithm conjectured. Now let me introduce learning augmented online algorithms to you. And for what we will review what we have seen so far. So we have seen an online problem with some online input. And we have also seen a classic online algorithm like double coverage, which solves the problem. And this algorithm is robust because it has this hard competitive ratio, which tells us that it won't be too bad compared to an optimal offline solution for any instance. But on the other side, classic online algorithms are often perform poorly on easy instances, where it would be, for example, the best idea to just move the closest server towards a request. But there are also other ways to solve such problems. For example, we could train some machine learned model to predict us the online input or predict something else, which may give us valuable information for a possible solution. But the problem is that there's no guarantee that this information is actually good. And this is a problem in, for example, safety critical applications. And this is the place where learning augmented online algorithms come in. And the idea is really that they combine the best out of both worlds. So on the one side, they use the valuable information from machine learned models. On the other side, we want that they use classic robust methods of such classic online algorithms. And we use two performance indicators to analyze such algorithms, namely consistency and robustness, where we say that a learning augmented online algorithm is alpha consistent if it is alpha competitive for having perfect predictions. Which means that if the prediction is really good, or essentially best possible with respect to our prediction model, we want that the algorithm should also perform really well. So think of this alpha should be really small, and it should, for example, break existing lower bounds in the online model. And on the other side, we still want our algorithm to be robust, which means that it should be better competitive for any prediction, which then says it just should be, for any input, its cost should not be much worse than the ones of an optimal offline solution. And learning augmented online algorithms are a very active research area right now, where almost daily there are coming new results for various online problems, but also for in other areas of computer science. Now our goal is to apply this framework to our problem. And first of all, we need a prediction model. And we choose the prediction model which predicts which server we should use to serve a certain request. So think of the following setting: when a new request arrives, the prediction model will give us a prediction on which server we should use to serve the request. And this is kind of a prediction of algorithmic actions. But the prediction model is also compatible with input predictions. So if we have predicted some online input of requests, we could just compute the optimal solution based on this prediction, and then use this optimal solution as prediction of our algorithmic actions. And we also show that these predictions are actually PAC learnable using empirical risk minimization. So using this prediction model, we can design our very first learning augmented algorithm, which is the naive one and just follows the predictions. yeah, so we just use the predicted server, which is encircled green here, to serve the request. And since I said before, it makes no sense that one server moves by another, we can just shortcut in the final schedule moves, which means that we then would just use the closest server of the request, which is on the same side as the predicted server, to serve the request. Now we have seen two algorithms for our problem. One is follow the predictions and the other one is double coverage. And yeah, follow the prediction essentially fully trusts our prediction because it exactly does what it tells us. And we can also see that if the prediction is correct, so if we really predict an optimal solution, we've just followed this optimal solution, which means that we are one consistent. But on the other side, there may be instances and predictions which lead to just unbounded costs, and which means that our algorithm is not robust. And on the other side, we've seen double coverage. So if we give double coverage also the predicted server, it would just ignore it. So it doesn't trust the prediction at all. And yeah, since this is k-competitive, it is then just k-consistent and k-robust. Now to get so our wish would be to get an algorithm which kind of uses properties of both of these approaches. And the idea here is that we want to balance how much we trust the prediction by using speeds. And the algorithm which we come up with and we call lambda DC is the following. So first of all, use a hyperparameter lambda between 0 and 1, which kind of expresses how much we trust the prediction. And we then do the following. When a new request arrives, we move the server which is on the same side as the predicted server with speed 1, and the server on the other side with a lower speed lambda. So if we set lambda to 0, this means that we fully trust the prediction. This algorithm corresponds to follow the prediction. And if we set lambda to 1, which means that we have no trust into the prediction, our algorithm is equal to double coverage. So this algorithm kind of interpolates between follow the prediction and double coverage using this hyperparameter, which sets the server speeds. And yeah, what we would hope for now is that also the performance guarantees for lambda DC interpolate between the ones of follow the prediction and double coverage, depending on lambda. And indeed, we can show the following. And we will now first look at the results for having two servers and later generalize to k servers. So for having two servers, we have the following result. For any lambda between 0 and 1, our algorithm is 1 plus lambda consistent and 1 plus 1 over lambda robust, which is kind of what we expected. Now, this theorem is nice, but it only covers the extreme cases. So for example, imagine we've given some prediction where almost every server is predicted correctly except one. Then the prediction is no longer perfect, which means that this theorem would only give us the robustness ratio. But we would actually expect that the algorithm on this almost perfectly prediction may performs really well. And so we expect that the performance should be close to the consistency case. And yeah, to cover these results in between, we define the prediction error, which tells us how good our prediction is. And we have two possible definitions for this error. First one is to just measure the difference in the cost of following the prediction and the cost of an optimal solution. And the second definition is to sum up the differences between the configurations of following the prediction and the ones of a fixed optimal solution, and sum this up over all requests. And using one of the prediction errors, we get the following theorem, which states that for any lambda between 0 and 1, lambda DC has a competitive ratio of at most the consistency ratio times 1 plus the relative prediction error, where the relative prediction error is just the prediction error divided by the cost of an optimal solution. So if the prediction error is 0, which just this gives the consistency ratio. And the second part of the competitive ratio is then just the robustness ratio. Now, for the remaining talk, I'm going to give you an idea on how we can prove this theorem. And there we will use the following three-step analysis. In the first step, we bound the cost of our algorithm using the consistency ratio and the cost of following the prediction. In the second step, we bound the cost of following the prediction by the cost of an optimal solution and the prediction error. And finally, we independently prove the robustness ratio by comparing the cost of the algorithm to the cost of an optimal solution using the robustness ratio. And clearly these three steps give the above theorem. And for the general case of having K-solvers, we will also use the same three-step analysis. So the second step immediately follows from the definition of the prediction error. So in the following, we will look at the first step, and then also quickly at the third step, as it is very similar to the first one. So what we want to prove in the first step is the following lemma, which states that for any instance I and then any lambda between 0 and 1, the cost of our algorithm are at most 1 plus lambda the cost of following the prediction, plus some additive constant. And our three main ingredients of this proof are a potential function phi paired with the folklore lemma for solver problems, which is also known as the interleave remove technique. And this works as follows. So if we want to compute a competitive ratio between two algorithms A and B, we simulate both algorithms in parallel on the same instance, and then use the potential function to map the states of both algorithms for any point in time to a potential. And then we have to do the following things for every request. We first let the algorithm B serve the request. And then we have to check if the change of the potential function is bounded by some constant A times the cost this algorithm charged for serving the server. And secondly, after B served the request, we let the algorithm A serve the request. And then we have to again to check if we can lower bound the decrease of the potential by some constant B times again the cost the algorithm charged for this move. And if we have these two bounds for both moves, we immediately get a competitive ratio between both algorithms for the whole instance. And our third ingredient for the proof will be that we have advanced knowledge about FTP server positions, depending on how our algorithm executes its move. Okay. Now let's quickly dive into the proof. So denote the servers of the algorithm by S1 and S2, and the servers of following the prediction by X1 and X2. Then we define the following potential function, which follows the classic style of having a matching part, where we compare the positions of the algorithm to the positions of FTP and scale this up using a factor depending on lambda. And the second part, the spreadness part, just measures the distances between the servers of the algorithm, which is in the case of having two servers, just the difference between both algorithms. So this is our potential function. Now, we apply the interleaving move technique, and we assume that some request arrives, and we first let FTP serve the request. So let's just assume that FTP uses server X1 to serve the request. And the worst case, so we have to upper bound the change of the potential now. So in the worst case, the server S1, which is matched to X1 in the first part of the potential function, is somewhere on the left, which means that the distance between both just increases by the whole cost of this proof. And this immediately gives us the upper bound, where we just have to add the factor of the matching part of the potential. Okay, now in the second step, the algorithm serves the request. And for now, assume that the left server is predicted as 1, which means that this server moves with speed 1 towards the request, and the other server moves with speed lambda to the request. And we can assume by scaling, but these are the actual distances both servers move. And since we assume that S1 is predicted and FTP already served the request, we know that the server of FTP, X1, must already be on the request. This means that the distance between S1 and X1 due to this move decreases by 1. But the distance between S2 and X2 may increase by at most lambda. So this is essentially the change of the matching part due to this move. And the change of the spreadness part is just that it decreases by 1 plus lambda, since both servers are moving towards each other. And this then just gives a lower bound of 1 over lambda times the cost of the algorithm on the decrease of the potential. And in the final step, we can just divide these two factors and get our consistency ratio. So this was a short sketch on the proof for the consistency case. And now we want to quickly look at the robustness proof. So this looks very similar. Here we are comparing the algorithm to the optimal solution. And we will almost use the same potential function with just a slightly different factor in front of the matching part. And so what really changes here is that in the second step, when the algorithm serves the request, we don't have this knowledge of which server of the optimal solution is actually on the request right now. So here the worst case changes to that actually server X2 is on the request, which means that the distance between X2 and S2 decreases by lambda, but the distance between X1 and S1 may increase by 1. And then we get some different constants in the lemma, but we can still prove the robustness ratio of 1 plus 1 over lambda. Okay, now let's look on at the general case. So we can generalize these results to the case of having K servers, where we have the following ratios. So our consistency ratio will be this alpha K expression, which is essentially 1 plus lambda for K equals 2. It's 1 plus 2 lambda for K equals 3. It's 1 plus 2 lambda plus lambda squared for K equals 4, and so on. And our robustness ratio will be just the sum of the flipped powers of lambda from 0 to K minus 1. And yes, so we have then the same error dependence of the prediction error. And we achieve this result by, as I said before, using the same 3-step analysis, but we have to use way more complex potential functions, which still consists of a matching and a spreadness part. But for the consistency case, we actually have to use additional weights inside the spreadness part. And for the robustness proof, we have additional server-dependent weights in the matching part. This allows us to prove the theorem with technical care. Okay, so then let me conclude. So we have seen that there exists a learning augmented algorithm for the K-solve problem in line, which is consistent, error dependent, and robust. And yeah, which implements its confidence with the prediction into the classic double coverage algorithm using different server speeds. And further results of our work are that we prove that this algorithm has a best possible consistency robustness trade-off up to a factor of 2 among all memoryless algorithms that satisfy some locality properties. And we also conduct empirical experiments which show the superior performance of our algorithm on real-world instances compared to the classic double coverage algorithm and other learning augmented algorithms which work for our problem. And the experiments especially show that already a small amount of non-trust or a small amount of robustification help to robustify the algorithm against errors, which we can see here. The green line is just following the prediction where lambda is 0, but already setting lambda to 0.1 drastically improves the performance also for large relative errors. Yes, then that's all I wanted to say. Thank you for your attention.